Hi ChemComm. Earlier in Unit 6, when we were talking about nuclear chemistry, we talked about how a radioisotope decays by alpha emission or beta emission. Today we're going to talk more about how we can detect how long it will take for that decay to occur. Let's get started with talking about half-life. Half-life is simply a measurement of time. It tells us how long it takes for a sample of atoms, a sample of radioisotopes, to decay to the point where you only have half of that sample left. So for instance, if I have 100 atoms of polonium-214, it would take 1.5 times 10 to the negative 4 seconds to get down to 50 atoms because the amount was cut in half. In the same way, if I had 100 atoms of uranium-238, it would take 4.5 billion years to get down to 50 atoms. So the sample needs to be cut in half, and it's the time it takes for that to happen. And every radioisotope is different depending on the instability of that specific radioisotope. All half-life graphs look similar to this. They start off with some amount of a radioisotope, and then over time they cut that amount in half, and then half again, and then half again, and then half again. If you're thinking about that, if you keep dividing by 2 on your calculator, you would expect that you never get to 0. Mathematically, that might be correct, but with atoms, you'll get to the place where you have 1 atom left and it will eventually decay. You can see that based on this chart, the time it takes for this sample to be cut in half is 30 minutes. Here's a bunch of other radioisotopes and the times it takes for them to be cut in half, or their half-lives. You can see uranium-238 is 4.4 billion years. You can see thorium-234 is 24 days. You can see things that are 1.1 minutes, and you can see things that are microseconds because they are so unstable that they decay so quickly. So every radioisotope is different. It's about the stability, and they all have their own unique half-life. Today I want to show you a method of how to calculate different variables within a half-life scenario. There are equations that help us do this, but we're going to use more of a graphic organizer approach. You can kind of think about this as an umbrella. The umbrella looks like this. On the top of the umbrella, we have total time. This is the total time it will take based on the scenario. On each one of these little segments in the middle, that's the half-life time. That's how long each half-life will be. And then we put the mass down here at the bottom. The starting mass will go here to the left, and the ending mass will go here to the right. So let me show you how this works. In our above problem, it says the half-life of C14 is 5,700 years. It says we have a 1,000 gram sample of C14 and would contain only 500 grams of C14 after 1 half-life. So in this scenario, the total time that they're asking about is 228,000 years. The starting mass is 1,000, and then we have to figure out how many times we can go through a half-life. The first half-life would be 5,700 years. If you type that into the calculator and you add another 5,700 years, you'd get 11,400. After a third half-life, you'd get 1710. Sorry, I made a mistake. This is not 200,000, it's 22,000 years. And then after the fourth half-life, we'd get a total of 22,800 years. So now we know that 4 half-lives can fit into that 22,000 years. So now all we have to do is divide that starting mass by 2 that many times. So after the first half-life, how much is left? Half. So 500. After the next half-life, how much is left? Half of that, 250. After the next half-life, we'd have 125. And after the final half-life, we would get 62.5 grams. So that's kind of how you use that graphic organizer to solve those problems. Let's try a different one with a different unknown. If you have 16 gram sample, so right off the bat, we know our starting mass. And it decays to 1 gram. So we know the ending mass, which is going to be 1 gram. After 40 days, So we know that the total time is 40 days. So we have to figure out how many half-lives have occurred. Well, after the first half-life, how much would we have left? 8 grams. After the next half-life, how much we have left? 4 grams. After the next one, 2 grams. And then after this one. So if you look, we have 1, 2, 3, 4 half-lives. Well, if my total time is 40 days, I know that my half-life then, if there's 4 of them, has to be 10 days, which means that every 10 days, the amount gets cut in half, or half of my radioactive isotope decays. In the activity, there's lots of examples of this. Practice them, get good at it, ask me questions if you have them. Have a good day. We will see you soon.